Maybe we should do this. Okay. Okay. I have too many things on me. Just a second. Oh, no. So let's continue. So this morning we managed to find the exact propagator for the quarks. So that was our result. And we found this formula. And there is this K, of course, is the momentum. There is 2K plus K minus. And then we have this IR divergence, which we can interpret as telling us that the quarks don't want to exist as asymptotic states. They don't want to exist, but still we can do calculations with them. And this mi squared is sort of a normalized mass, which is the 3-level one that we put in our Lagrangian, plus g squared n divided by pi. Perhaps I didn't say that, let me say it one more time in case it was not clear, like we are doing the Lagrangian with this combination fixed, right? So this is order 1 in our scaling. It's our 't Hooft coupling. And we gave a name to this guy. We called it delta ij si of k. Now we need to proceed because so far we didn't yet get to some physics. So to proceed, we need to resum. We want to resum the ladder diagrams. So let's draw again some blob. This is going to be our exact 4-point function at leading order at Lagrangian. And what is going to be the equation for this? You see, it's very natural to write this kind of equation in which we have just the exchange diagram, right? And then we have just one, remember the English term of this, like one thing of the ladder, and then we put again our blob. Okay, so with this kind of equation, you see that we are just basically saying, that the blob is equal to this plus this plus this and so on. Okay, the infinite sum. And I forgot something. What I forgot to say is that now when we draw these diagrams, we are now this line is the exact propagator. Okay? But since I don't want to keep drawing the gray blobs every time, I'm just gonna use a simpler notation, okay? But remember that now on the internal lines, we're gonna put the exact propagator of the fermion. And in this resummation, again, remember that we are using planarity, and I just want you to realize that, like, planarity meaning the large n, planarity forbids contributions like this diagram, okay? So the reason why we have this simple structure is because of large n. We don't have to cross the legs, or we don't have to consider things like this. And another thing that we can avoid considering is, which I want to draw your attention to, we can also avoid considering stuff like this. Imagine that we have here a loop of the fermions running inside. So you see diagrams like this that we are neglecting thanks to large n make it clear that if we would be at finite n, I mean, formally it would still be possible to write some kind of self-consistency equation, but our self-consistency equation will be forced to include also, for instance, 6-point diagrams in which you see I have 2 quarks, and then at some point there are 4 quarks. So it's a 2 to 4 kind of process. And it's only thanks to large n that these 2 to 4 are forbidden. So at finite n, it is still possible, in principle, to write down a self-consistency equation, but it would involve for instance, stuff like, so if I'm trying to, now I will write explicitly how many fermionic legs there are. So this guy would also have some contribution with 2, 6, right? I would have something like this, and then trying to write down some equation for this, we would also need, and then for this, we would also need eight, and so on. Okay? So it's only thanks to large n that we can write down a simple equation that only involves the 4-point function. And let's make it clear also how we are going to go from this to the mass of the mesons. So again, the idea is that we want to find bound states, right? Oh, I cannot find the good chocks anymore. Okay. And so what we want to do, we want to solve that and then look for some particular contribution. When we have that blob, when we have this blob, if we call R the total momentum that is entering. I just wanted to point out that it's only thanks to Largen that the equation closes for this black blob, okay? Otherwise, you would get an infinite system of equations which you need for the 4-point function, you also need the 6-point function. For the 6-point function, you also need the 8. I just want to say that there is nothing special about Largen in the fact that we can write a self-consistency equation. What is special is that it truncates only at the level of the 4-point function, okay? And so we can write it, like really it makes it useful, because otherwise it would be impossible to make progress. Okay, let's see if I manage. Wow. Yes? Okay, yes, so we need to be a little bit more, we need to extend a little bit what we mean by planar. In this case, when we have both gluons, let's say object with 2 indices and object with 1 index, okay? So you might have seen the argument for why, if you have just matrices, then it's organized in a topological expansion, the diagrams. And in the case where you have fundamental matter, you need to refine a little bit that argument and allow also boundaries for surfaces. Okay, so just like you have accounting for how many handles your surface has, you also need to start counting how many boundaries you have, and the boundaries are associated to the fundamental particles. And the more boundaries you add, the more factors of n you get in the denominator. Okay, so here I'm adding a boundary to my surface. You see, this is my surface, and I'm cutting a hole inside, so it goes down. And so what are we looking for? We are looking for some contribution that goes like this. If R is the total momentum, we look for 1 over R squared plus mu squared minus I epsilon. Okay, so this is a pole, and the position of this pole tells us about this is the mass squared of a quark, anti-quark bound state. Okay, i.e. the mass square of the meson. Okay, so this is not different from when we discussed the Gross-Neve model in 3 dimensions. Also there, what did we say? We said that we scatter the fermions, and then we saw that there was this pole, right, which was precisely a threshold, and then we said this is a bound state. And this is the same thing here. So what we expect is that we're going to have poles, and these poles are going to tell us about the mass of the mesons. And we can already anticipate that, you see, if that's our equation, we are going to see that appear, but you can already anticipate that what we want to find is a pole, right? So as it stands, this is a, you can understand it as a linear equation for the gray bubble, for this object. It's a linear equation with an inhomogeneous term, right? There is a source, let's say, that is the 3-level exchange. However, when you go to the pole, it means that this object is having a divergence, right? And when it has a divergence, you can forget about this inhomogeneous term. And so it takes, you already see from here that it's going to take the form of a eigenvalue equation, right? You have that convolving your sausage with an exchange, you get again your exchange, okay? And this is sometimes called Bethe-Salpeter equation. It's the Bethe-Salpeter equation for the 4-point function, which determines the bound states. Okay. So now this was a bit of introduction, but let's start doing the computation. So, is there a question? Ah, I didn't see. So I'm just saying that what we're interested in is a contribution in which the sausage is diverging, is the pole, right? And this doesn't have this pole. So I'm just saying that when you go to the pole, it just becomes an eigenvalue equation, basically. It tells you that convolving your sausage with this gives you again, okay? Now, yes, I wanted to write here. So if we call this with the fermionic indices alpha, beta, gamma, delta, if we call it gamma minus, then by doing the same trick that we did today of getting rid of the indices by taking traces, right? We take the trace with gamma plus and the trace with gamma plus on both sides. Then in the simplified notation without fermionic indices, this we can write like this. So I, J, J. Let me call this momentum P. This momentum R minus P. You see the total momentum that enters is R, and we're looking for poles in the variable R. And what exits here, let's call it P prime and R minus P prime. And this, we can give it a name as Tij of R, P, and P prime. Okay? And now let's go ahead and compute this contribution. So what is this going to be? Again, since I want to equate, I need to put P and P prime, and oh, so no, it's not P prime, this is R minus P prime, and this is R minus P. And let's call this internal line K, and as a result, this is going to be R minus K, right? R minus K, and what goes up here is K minus P. Okay? And so let's go ahead and write this diagram. You see we have an undetermined momentum K, so we need to do an integral in d2K over 2 pi squared, and we have two vertices and the propagator of the gluon and a closed loop. Okay, if you write this in double line notation, so they together they give us this prefactor K minus minus P minus squared. Okay, so this is vertices, gluon propagator, and they also include the closed loop. Then what do I have? I have two exact propagators of the fermion. I need to put one here and one here. And luckily I introduced a notation, so I don't have to write down a very long formula. So I have Si of K, I think, yes. So this was the I line, and this is the J line, okay? I have Si of K, and I have Sj of, for some reason I wrote K minus R. Ah, yes, there is a reason. The reason is that I forgot to draw the lines, you see. This goes like this, if you read the arrow. And so you see that if you follow the arrow, this is k minus r. So there is Sj of k minus r, okay? And then we have again 4 Tij. And now, this time this is of r, k, and p prime. Okay? Now, we are going to do some naming things. Oops. Let's name this thing here. Okay, so Sij times Tij. Let's call it, psi. Okay, this is really the notation in Toft paper. R, K, P prime. Okay, let's call it psi. So if we call it psi, equating these two guys, we get this equation. Psi ij of r, p, and p prime. So for now, we still keep around the three-level exchange. So the three-level exchange, which is the inhomogeneous piece in our equation, right? The inhomogeneous piece in our equation is the three-level exchange, and now the equation is like this. I think this should really be p minus r. I think I have a mistake in my notes, sorry. P minus r, then there is a g squared times p minus p prime minus squared. Okay? And there is then plus, actually, sorry, minus I. So where does the I come from? Where does this I come from? It's because I'm rotating to Lorentzian, my integral. So this comes from Lorentzian. Okay. The Feynman rules, remember that the Feynman rules that we wrote were all Euclidean. So when I rotate to Lorentzian, I get these factors. And then I have an Si of p, Sj p minus r, times what? The integral in dk plus dk minus over 4 pi squared. This is the Lorentzian measure, right? We split k plus and k minus. And then we have 4g squared n over k minus p minus squared times psi ij. Okay, so with this trick we just put the s outside. That's all we did. Nothing special so far. So questions until now? Sorry, bear with me. Now it's going to be a little bit of a calculation, but yes? So this thing which is inside this is supposed to be red or pink, but probably it's not distinguishable from white. So this thing here, I replace it with psi. Okay, so what did I do now? I took my equation over there, the one in the box upstairs, okay, and I wrote it, and then I multiplied everything by SS, okay? So when I multiply the first thing by SS, I get psi. When I multiply the three-level exchange by SS, I get this. When I multiply the second piece by SS, I get this. Okay? Good. What do I want to do now? The other thing that I want to do, you see, I want to use the fact that here I have this guy which only depends on k minus, and the dependence on k plus is only here. So to simplify a bit our life, what we are going to do is to actually perform this integral over k plus. Okay, just the one over k plus. We are going to perform it. And there is going to be another naming step. So we are going to give it a name. So let's call phi ij. This is just now a function of, so phi ij r p minus p prime is defined to be the integral over dp plus over 2 pi of psi ij. Okay, so clearly this thing doesn't depend on p plus anymore. So on the complicated term, let's say this one, it's immediate to get phi. I just need to perform this integral, and that's the definition. But I also want to have phi here, right? So how can I get a phi here? I need to take my full equation and apply this integral to it. Oops, apply this integral to it. Okay, so now I'm going to take my equation and apply this integral in dp plus over 2 pi to the three components. Let's do it. Let's do it. Where do we do it? I think that blackboard up is a bit useless. So I want to write in terms of this phi. Okay. So we apply this guy to our equation, this integral. Yes? There is no 4. You are right. What did I do with the 4s? No, I think I just erased 4s all over. You see? The three-level exchange also has a 4. Because, because the vertices are 2, right? Are 2i. The vertices are 2i. Yes. So the 4s should work fine. They should take care of themselves. Okay, so now I apply this integral, and what do I get? I get phi ij, so the first part is easy, I just get phi. That's my definition, so I don't have to do anything. And the nice thing is that both here and here, you see, where is the dependence on p plus? It's only in my exact propagators, right? So it's going to somehow factor this integral. I'm going to have a integral on dp plus over 2 pi of s of p minus r. And let me put some bracket here to make it clear that this is the only thing we are integrating over p plus. Okay? And then there is a g squared p minus p prime minus, okay, so this is just minus squared. And similarly, in the second term, I have minus I, exactly the same bracket, integral in dp plus over 2 pi s of p minus r, right? Of what? And what I'm left with is the integral in dk minus of 4g squared n over k minus p minus squared times phi ij. So you see the magic that happened? The magic that happened is that I started with an integral equation with two integrals. And now, just by doing some redefinitions and using the fact that many things don't depend on the plus components of the momenta, if I now manage to perform this integral, which is in terms of explicit functions that I know and I've already computed, the final integral equation that I'm left with is just in one variable, right? I just have one integral here. I don't have any more two. Okay, so I'm very happy. And now we need to take some time to compute this integral in the bracket. So let's do it. After we compute the integral in the bracket, basically we are done. Everything is clear so far? Questions? Okay, so we proceed to do that. Let us go ahead and compute that. Did we? Okay. So the integral in the bracket is just this. It's an integral in d pi plus over 2 pi. We have two factors of minus I from the two propagators, so let me put them together. And in both the numerators, we have p minus or p minus minus r minus. I'm going to divide numerator and denominator by that for my convenience. So one propagator now looks like this. So look what I'm doing now. So I have this expression, pi lambda minus I epsilon. And here I will just write sine of p minus. So where are these two factors with the sign of p minus? One is because here, you remember, I had an absolute value of p minus, right? And I just rewrote it as p minus sine of p minus. Okay? So when I divided by p minus, I just remained with the sign. Where does this epsilon sine of p minus come from? This comes from this not very deep equation, that if I have epsilon divided by p minus, this is equivalent to just epsilon times the sine of p minus. Because you see, epsilon, the only job that does, it's giving us a sign. Either we go a little bit above or below. So this sign is now determined by the sign of p minus. Is it clear? So I can replace it with epsilon times the sine of p minus. Okay, so if this is clear, let me now write the second propagator. Sorry, this was just an explanation. And the second propagator is the same thing, just with the other momenta. We have p minus minus r minus plus 2 p plus 2 r plus. And now we have plus g squared n over lambda minus I epsilon times the sine of p minus minus r minus. Okay. So we have to do the integral in the variable p plus, which appears just here. and here. Okay, so it's a very simple rational function, which we can do the integral like using the complex plane. And let's do it here. And maybe I should remember not to erase that. Okay, let's try to remember it. So what's the structure of these poles that we have? Okay, this looks good. So the structure of these poles is like this. So now let's look at the poles in the pi plus plane. So you see now the sign depends where the poles are in the complex plane. This depends on these two signs that we have. So there is, the first possibility is that not really sure here I have all the possibilities. Ah, yes. I just need to look at, for instance, the one case is this is plus and this is plus. Okay? So if they're both plus, it means that pi minus is bigger than 0 and pi minus is bigger than r minus. Okay? Then you see that both of these poles are in the upper half plane, right? And I'm integrating over here. Okay? So what am I going to do in this case? In this case, I'm just going to close the contour here and get a wonderful 0 as an answer. Then there is, let's leave the most interesting case in the middle. There is, of course, the other possibility in which p minus is less than 0 and p minus is smaller than r minus. And now you see that all of these, both of these poles are going to be here. And I can take my contour and close it in the upper half plane and again get a 0. So in these two cases, the integral gives me 0. So the only case where I get non-zero is one pole is up and the other one is down. Right? So if I have one pole here and one pole there, then of course I should really draw these poles infinitesimally close to the axis, but okay, it's just the only thing that matters is in which half of the complex plane they are. So for the purpose of drawing, I can draw like this. And now it doesn't really matter whether we close up or down, but we're going to get a non-zero contribution, okay? And this is in the case 0 less than p minus less than r minus, or r minus less than p minus less than 0. If I did my inequalities correctly. And I think I decided that I will assume, since r is our external variable, okay, let us be definite and assume that r minus is positive. So assume r minus, let's compute our function when r minus is positive, so we don't have to keep distinguishing all these cases and get crazy. So let's assume that r minus is bigger than 0, and then p minus is gonna have to be between 0 and r minus. Okay? And I think I can erase here. Yeah, sorry, we have to suffer a bit, but then it's going to pay off. Okay. So only contribution from 0 less than p minus less than r minus. And then it doesn't really matter whether we close up or down. And let me just write what is the answer. Let's see. Let's say we close up. Then we get a 2 pi I, right? Because it's going to go in the clockwise, counterclockwise direction. So I get a 2 pi I. And there is a minus from this minus I squared that I had there. So there is a minus 1 over 4 pi. Where is this 4 pi coming from? Let me think. Might have forgotten some 2. It's just because we have a 2, you see, in our variable. So not too mysterious. And then we have, just to compute, so in this case I get the pole from the first, function, so I just need to compute the second at the pole, okay? So it's gonna be this. Let's see if you agree. Let's see if you agree. I need to evaluate this at the location of the pole that I have there in the first denominator. So pi plus equal 1/2 of minus mi squared over p minus g squared n over pi lambda. Okay? So that's my residue at the pole. Okay? Good. So what do we get? Eventually, we get minus I over 2 from these two. 1 divided by mj squared divided by p minus minus r minus mi squared divided by pi minus plus 2 r plus minus 2. Unfortunately, we might have hoped that these offensive divergent terms would cancel, but they don't cancel quite yet. Plus I epsilon. Okay, so let me stop for a second because this was a bit of a calculation. Are there questions about this? So is it clear what we did? We just picked the pole in the upper half plane and we computed the residue. And the residue is just the second fraction evaluated at the position of the pole of the first one. Okay, are we happy? So if we are happy, what we did now was to compute that bracket, right? So what's the simplest way to now rewrite that equation? Since this bracket beautifully came as 1 over something, we're just going to bring it to the first side of the equation, okay? Let's bring it to the first side of the equation, and we can write the result. So the result is 2i, which is famously the inverse of minus I over 2, times 2r plus minus mj squared divided by r minus minus p minus mi squared divided by p minus 2g squared n over pi lambda, okay, times our phi ij. I will not write the arguments of phi ij just to save some space. This is equal to g squared over p minus p prime minus squared, okay? And then we have just one integral. The integral okay, over our of our phi ij. So let's put some color or something here. So it's a beautiful equation. And that's our equation for phi ij. But there is still something that we can do about it. So you see, this phi j is supposed to encode some interesting physics, and it's very annoying that we still have this IR cutoff hanging around. It's very annoying. But then there is some hope that appears when we realize that this integral that we have on the right-hand side, you see, it's at least assuming that this phi is some kind of regular function, then here we still have an IR divergence, you see? When, maybe I should put it up. When k minus is approaching p minus, sorry. When k minus is close to p minus, this integral diverges. And that's also an IR divergence, right? Every divergence that happens at finite momentum, we call it an IR divergence. And so the next step we are going to do now is to somehow try to separate from this integral some piece which is IR divergent and some piece that is finite. And hopefully, when we separate this IR divergent term, we finally we're going to get rid of all the IR divergences in our equation. Okay? So now we are going to open a small parenthesis to get rid of the IR divergences. Actually, this is the oldest one. So let's see how to get rid of them. So the type of integral that we have on the right hand side let's simplify it a bit so we can really extract the useful information. So the integral is something like this. So with our IR cutoff, call it lambda, we are carving out some small interval around the divergent piece, and we have an integral like this. Okay, so now I'm just writing phi of x to simplify the notation. And we want to separate the IR divergence from the finite part. So there are perhaps many ways to do it, but one way we can do it is as follows. Let's remember something which is certainly finite, which is the Cauchy principal value applied to some function. Okay, so this integral is finite. So if we do principal value of 1 over x minus x naught, and we apply to some function. And we can also rewrite this formally using our IR cutoff. How do we write it? We write it as the limit of this IR cutoff going to 0 of the integral in which we carve out some small interval of 1 over x minus x naught times our function. So what's the magic why this kind of integral is just finite by itself? It doesn't have any IR divergent piece. Well, the magic here is just that the reason why this distribution is famous and has a name is because it's finite, and it's finite because, you see, 1 over, if we have our point x naught, let me do some drawing. So this is x naught, and this thing just behaves like this, right? The function 1 over x minus x naught. So we are basically doing this symmetric limit. We are erasing some positive infinity with some negative infinity, and we are faking it like if they give 0, okay? So that's the procedure that gives us this finite integral. If we do the same with the square, clearly this doesn't work, right? Because we have 1 over x minus x0 squared, then this thing is positive on both sides. So that's why actually this integral contains a divergence, while this integral doesn't contain a divergence, okay? So, however, one thing that we know is that once we have a distribution that is finite, another thing that is finite is the derivative of a distribution. Okay, so that's something that mathematicians tell us that it is still finite, so we're happy. So So how is this defined? We might denote it like this. We call it P of 1 over x minus x0 squared. Okay, so this is something that is supposed to give us a finite answer. And sometimes I've also seen this thing called, instead of Cauchy principal value, Hadamard principal value. So if you want to give it a name to look fancy, you can call it Hadamard principal value. And so this is just defined as minus the derivative of this other distribution. Okay? What does this mean to take the derivative of a distribution? So what is the definition of this derivative? Defined by integrating by parts when applied to test functions. Okay. So let's see what we get if we use this definition. Okay. So we want to use this because we know that this gives a finite contribution. And now we want to rewrite our IR cutoff integral as a finite contribution plus a divergence. So if we apply this to a distribution, sorry, to a test function, okay, so this is by definition, we define it to be the derivative of that. So this gives us this formula. So this is just the principal value applied to the derivative of phi. Okay, so that's just a definition. Did I miss a minus? No, I think I didn't miss minuses. Okay, so that's just the definition. Now this, we know what it is. This is just the limit for the IR cutoff that goes to 0. The limit for IR cutoff that goes to 0 of the integral for x minus x naught bigger than lambda of the integral of the derivative of phi. Okay? So now maybe I will spare you this, but what we can do now is that we can just open up this, right? Write it in two pieces, and in each of the two terms we integrate by parts, okay? So if you do this calculation, you're gonna get that this is equal to the limit for lambda going to 0 of the integral of, so here we are skipping some steps, but you can try to, you can fill in the calculation here. It's not hard. So you can just see that this is equal to this. This is precisely our IR regulated integral. This is our IR regulated integral. Minus, you get an additional 2 over lambda phi in the point x naught. Okay, so that's our IR divergence. Okay? So in other words, our IR regulated integral, we can rewrite it as this Hadamard principal value plus 2 over lambda phi in the point x naught. Okay, so let me write it here. So in other words, our integral with IR cutoff is equal to this finite piece, no, yes, is equal to this finite piece plus 2 over lambda phi of x naught. Okay, so we extracted the finite piece. Okay, the chalk is gone. We extracted the finite piece and the IR divergent one. And now you see that if you put it in that box, the question that we have, we are extremely happy because it should precisely cancel the IR divergence that we have in the first side of the equation. So there is a 4, but there is also a 2 pi, right? So if you look at all the factors of 2, they work out nicely. And eventually, the IR cutoff is gone, okay? So the IR cutoff disappears from our equation, and now we get a beautiful equation without any IR divergence. And let's write the beautiful equation here. We are going to do a further thing, which is to, let's also multiply by, I will write it here, we also multiply everything by r minus. Okay, let's also multiply everything by r minus. And finally, we get two r plus r minus phi ij is equal to so if I want to be super precise, let me be a little bit precise here. I need to put some heaviside theta that implements my constraint. You remember we restricted to some range of p minus. So I skipped it before, but now I'm reputting it just because it's the final, almost final version of the equation. So, and then we have the masses and the mass, the terms with the masses. Okay? And then we have this integral with the Hadamard principal value. And to prepare for the next step, let me just already write the integration variable as k divided by r. Okay, and here is k minus divided by r minus minus p minus divided by r minus squared. And remember that in the way we are computing, this phi we saw that is only non-zero when these theta terms are satisfied. Okay, this phi is only non-zero in that interval. Okay, so let's box it again. Maybe the green is more visible. And you see that this guy that appeared here, this combination that appeared here is precisely r squared, right? The modulus square of the momentum that is supposed to give us the mass of the meson. So now, and I promise this is the last massaging of the equation. After that, we are just gonna, well, maybe it's not really the last. So let's do this. Let's call mu squared is the object we want to find, the mass of the meson in units of our coupling. Okay, so you see this is a dimensionless combination because you remember G squared has units of an energy squared. And then let's call the fractions of p minus momentum carried by the two quarks. So one we call it x, I guess, right? Yeah. And then the k minus over r minus, I call it y. And finally, there is an x prime, which is the external, sorry, the final fraction. Okay? So these are fractions of p minus momenta carried by the quarks. And let's also introduce a notation for these masses in units of our scale. Let's call them gamma. Okay? So now we got rid of some ugliness. And we got rid of scales. And the equation is like this. Theta of x, theta of 1 minus x. So everything now in our equation is supported with x between 0 and 1, okay? And then we have something that we call Hij applied to our phi ij. Okay? And this operator Hij is partly multiplication. So we have a multiplication by this plus a multiplication by this, and partly an integral. And the integral is this, just this Hadamard principal value. Okay? Is it clear? So what I mean by H applied to phi, H applied to phi here is just a multiplication operator, while here I mean that we need to put phi inside this integral, okay, in the last piece. You need to put phi inside this integral. And okay, let's give some interpretation to this equation. So you see now, when we want to find the, let's first do that step and then we do some interpretation. Are there questions so far? Because phi itself scales like 1 over n, right? Because it was this, you remember that all the diagrams that we are resumming, the connected one, they all scale like 1 over n. Yes. In other words, it must be from this equation that phi scales like 1 over n, because the only non-homogeneous, the only thing that sets the scale of phi is the non-homogeneous term, right? And the non-homogeneous term scales like 1 over n. Other questions? Okay, and this is the mu is actually the guy we want to solve for, right? How long am I supposed to go ahead? Until 5:45, right? Okay. Now, so now this, we can imagine it as a problem for a function phi defined on x between 0 and 1. Okay, so that's our function. And suppose somebody, so this Hij is an operator acting on some space of functions on this interval, okay? Operator acting on functions supported in 0, 1. Okay. And suppose we are strong enough to diagonalize this operator. Okay. We are now going to make contact with the comments we made before about neglecting the inhomogeneous term. So suppose we diagonalize this, so we find some beautiful functions on 0, 1 that are eigenvectors of this operator. So that would be our dream. Okay, I'm calling them V because I want to stress that I think about them as eigenvectors of my operator. So I put them inside and I get some number. So this equation, we call it, it's what is sometimes called 't equation. It's the eigenvalue equation for this operator. And what should I erase? I think this is very old. And suppose that now I can find a basis of such functions, an orthonormal basis of such functions. So Vk orthonormal basis. And this basically, if I want to do that, it requires, what do I need to require? I need to require that Hij is a Hermitian operator. Okay? So then I can hope to find some orthonormal basis of eigenfunctions. And now they will satisfy something like this. Vk, a bit schematically, not taking into account possibly. Yeah, okay. So then once I have this thing, I take my phi and I expand it, right? I take my phi and I expand it in this basis with some coefficients. So this is my phi of x. I expand it in the basis, right? And I can also take my inhomogeneous piece of the equation, and I can go ahead and expand also that in the basis. Why not? Oh, this was a squared. And then I get some dk and then by doing this, you see, if I would be able to find such a basis of functions, I just turn my equation in an algebraic equation. Plugging back, I find something like sum over k of mu squared minus lambda k Vk Ck. Okay, I just use the fact that I diagonalize my h. This is equal to sum over k of Vk dk. Okay, so now I need to equate the coefficients. I need to equate the coefficients of my orthogonal functions. And I'm just basically saying the same thing that we said before in a different language. So by doing that, you find that your function phi is expanded in the orthonormal basis with coefficients that satisfy this equation. Okay, so you see, now this means that the location of the poles, you see I have a pole here in the variable mu squared. The location of the poles is completely determined by the eigenvalues of Hij. The inhomogeneous piece only gives me the residue. Okay, this is just again the same argument as before. You remember that I have this equation, and if I just want to know, well, I think I wrote it wrong. It's a more sophisticated way to write the previous argument, that when I go at the pole, I don't really care about this. I just care about the eigenvalue equation. See? This is now the eigenvalue equation for my sausage, and the inhomogeneous piece is not so important. Okay, so you see now the magic is all in these eigenvalues lambda. If I found the eigenvalues lambda, I have found the masses of the mesons. Okay? So that's really an interesting operator to study. And if you find a way to solve the eigenvalue equation for that operator exactly, it's nice. But now we are just, so let me tell you that we're not going to be able to solve the eigenvalue equation exactly today, but we're just going to use it to draw some conclusions about the spectrum of the mesons. Okay? We turn the problem of finding the spectrum of mesons at large n into the problem of diagonalizing an integral operator defined on an interval. Okay? Which seems much more manageable than what we started from. So now let's try to make it a little more precise. So you see, in these manipulations, I assume that H could be defined as a Hermitian operator, and also I basically assume that the spectrum in this is discrete because I assume that all these functions are normalizable, these eigenfunctions. So let's verify that this is indeed the case. Maybe I don't want to erase that blackboard, so okay, we have enough blackboards anyway. So the first thing that you can do is, what is the first thing that you can do? So we want to define Hij on some domain of functions of x. Sorry, before we continue, I forgot something. I wanted to give you some heuristic interpretation of this equation. So before we continue with mathematical blah blah, so let's give some interpretation of this. So the way to interpret this equation is that we did a lot of work, but actually the final result is pretty simple, right? So these two contributions, you know, we have our two lines that come and they form some bound state, right? And remember, x are basically the fraction of the incoming momentum that is coming from the two lines, okay? And it's basically like if we are diagonalizing, let me say it correctly, it's like if you're diagonalizing the p plus, okay, you can interpret it in this way, because you see this is like the mass of the first quark divided by this p minus, so it's like the p plus of the first quark, this is the p plus of the second, and so if we were just for these two terms, we would be saying something very silly, that you can just take the two quarks and put them together and form some composite state. And so what is this other term over here? So this other term over here is basically the non-local term, like this is mediated by the gauge field, okay? So this, in fact, you can also see it as a Fourier transform of the, you can also derive this kind of term by a Fourier transform of the linearly rising potential. Like the Coulomb potential in two dimensions is linearly growing in the distance. And if you do a Fourier transform, you get something like this, okay? So eventually this equation, even though we did a lot of work, is just telling us sum the two p plus and then add the term, which is given by the Coulomb interaction between the two, okay? Now, let's go back to our mathematical thing. So we want to find some domain of function, and we want that H sends this domain in itself, and it's symmetric, okay? So sending this domain in itself means that we need to ensure that if we take two functions, this thing is better be finite, okay? If we take the product between two functions. And let's write down what this looks like. So here I'm taking the scalar product to be just integral of f star g. That's my definition of the scalar product between two functions, okay? So when we do this scalar product, we get something like integral between 0 and 1 in the x of f star x. And then we have the term from the masses. So the simple term from the masses. I'm not sure I've been completely consistent throughout about what I call I and what I call j, but that's okay, I guess. So there is this first piece, which is the multiplicative part of the operator. And then there is the second piece, right? So let's make some considerations. You see, my principal value, when we derived it, started its life as an integral from minus infinity to infinity, but now I can restrict it to 0, 1, because anyway we said that everything here is restricted to 0, 1. Okay, so you see this first piece has the advantage that is clearly symmetric in f and g. This is a bit less. But one thing that this piece tells us is that to be finite, we better take f and g vanishing at the extrema of the interval, okay? So so this space of functions that we need to consider should be vanishing, at 0, 1, because we have these divergences, okay? And an exercise you can do, probably with Mathematica, probably it's better to do it with Mathematica, is to just what can you do? So you can say, okay, I want them to vanish, so we'll make them vanish with some power. So vanish at x equal 0, 1, like, for instance, you can take some power, x to the beta naught, and 1 minus x to the beta 1, okay? But then, I mean, if we want our eigenvalue equation to be solvable, it needs to be the case that when you take these guys and you compute their principal value, okay, you get something similar to dividing them by x. They need to be called the same order, okay? So you can do this exercise. Require that apply to them, apply to this behavior. Behavior gives x, which is what I get from the first. Or okay, if I want this to be eigenvalues, it needs to be the case that I can erase. So okay, what am I saying? I'm saying that, you see, we have an equation here in which h applied to phi gives us again phi, okay? So if phi behaves like this at the extrema, clearly when we apply h, naively it seems we have terms that go differently at the extrema, right? Because now we divided by this and we divided by this. So it needs to be the case that the terms that grow less fast are cancelled by applying this integral, okay? So if you require this cancellation, this gives a formula for this exponent, which hopefully I wrote. Gives you this. So this at least gives us some information about the space of functions. Just a calculation. This is just a calculation that you can do. Okay. And so now we took care of this finiteness of the first piece. We want to talk about the symmetry, okay? The symmetry is not manifest. The symmetry is not manifest, but you can make it manifest by doing some massaging. So basically, to make the symmetry manifest, add and subtract You see, there we have the P applied only to G, and you can add and subtract this term. the p now is here. There is 1 over x minus y squared. And I compute f and g in the same point now. Okay? So if you add and subtract this, and you massage a little bit, you find that that inner product is rewritten like this. You find that that inner product becomes gamma I plus 1 divided by 1 minus x plus, you see this plus 1 pops out, this beautiful plus 1. And then the second term, we can write it like this. Integral 0, 1 in dy, integral from 0, 1 in the x. And now it's f star x minus f star y divided by gx, sorry, not divided, multiplied by gx minus gy divided by, so since now I have zeros in the numerator, I don't need to really put anymore the principal value, okay? You see what I did? Before I had a term which had f in x and g in y. So I had f in x, g in, okay, this, yes. F in x, g in y. If I put a 1/2, I can also write a term with f in y, g in x. And then I added two terms with the f and g in the same point. Okay, I added two terms like that, and to subtract them, I also need to put this plus 1 here. Okay? And so what's nice about this is that now both of these things are positive definite, at least as long as, so we get that Hij is now written in a manifestly symmetric form, symmetric. We see that if you exchange f and g, this goes to itself, and it's positive as long as this gamma I and gamma j are bigger or equal than -1. Okay? So that's what we need in order to have, to ensure that the masses, okay, we would like the mass squared of our mesons to be positive, right? Otherwise we get tachyonic mesons. And that requires this constraint on the gammas. If you go back and look at the definition of these gammas, you remember what was this gamma? It was this capital M squared in units of the 't coupling. And what was the capital M? Was basically the small m in our Lagrangian plus some shift. Basically, what this -1 is doing is undoing the shift. Okay? So what we discover is that to ensure that the mesons are non-tachyonic, basically we need to put non-tachyonic quarks in our initial Lagrangian. Okay? So maybe, okay, let me just say it in words since we are basically almost at the end. So this constraint is like saying that the quarks that we put initially were non-tachyonic, and then we get non-tachyonic quarks. Now, before, maybe we're going to finish the comments tomorrow, but let me just say, how do we know? So we got, the first thing that we wanted to get was the symmetry and also the positiveness. And now let's comment a little bit about the discreteness of the spectrum. How can we convince ourselves of the discreteness of the how can we convince ourselves of the discreteness of the spectrum? I don't know where to erase. Okay, I can erase this. So a very qualitative argument is that this is a bit similar to solving a Schrödinger equation time-independent Schrödinger equation on an interval, right? And you look, our potential, this thing that we have is divergent on the two sides, okay? So one thing that we can argue, or let's say expect from this, is at least that we should have some discreteness at the bottom of our potential, some part of the spectrum which is discrete. So discreteness from the shape of the potential that diverges at the extrema. Potential in quote, if you want. Divergence at the boundary. But one thing that we cannot completely rule out from this is that we might also have some, for a larger part, for large eigenvalues, we might be not so sure whether we get also a continuous part of the spectrum. And so tomorrow what we're going to do, to finish, we're going to consider the end of the spectrum with, like, for large eigenvalues, okay? And we're going to see that all the way we have some discrete spectrum, okay? And we can get some very simple formula for the leading behavior when the eigenvalues are large. And yeah, and then we're going to conclude with our discussion of the Toft model. Okay. Questions? So the question that remains open at this point is, like, what happens for large eigenvalues? So this is what we're going to see tomorrow. Any question?